Okay, 9.3, graphing rational functions. Students will determine the vertical asymptotes and the point of discontinuity for the graphs of rational functions and graph rational functions. So a rational function is an equation of the form f of x equals p of x over q of x, where p of x and q of x are polynomial functions, and with q of x cannot equal 0, so the denominator can't equal 0. Rational functions may have breaks in continuity. Which means the graphs may have holes or points of discontinuity or asymptotes in them. Okay. Spelled that wrong. There should just be one S there. Okay. An asymptote is a line that the graph of a function approaches but never crosses or touches. So this is what's going to happen with these graphs. Let me just draw you a sketch. We're going to get something that looks kind of like this and kind of like this. And today we're going to find out that there's an asymptote, a vertical asymptote on most of these functions, that this graph will get closer and closer and closer to never touch. Also, sometimes we're going to find out that this graph is not, it's already not continuous because we have a gap here on this line. But we're also going to find out it's not continuous in that it's going to have little holes in it. And so we'll graph those holes like this. Here, I redrew it. See, the graph will go, and then there'll just be a little hole, and then we'll keep going. So we're going to figure out how to find these vertical asymptotes and these holes, or points of discontinuity. All right, so for this first one, we're just going to find any asymptotes or points of discontinuity. Well, here's the deal. Binomials, and it's not just binomials, but anything that cancels in the denominator create holes. So if it cancels out, it's going to create a hole. But binomials that do not cancel in the denominator, these create asymptotes. So let's take a look. Well, we could see right away that we would be able to write this as 1 over x minus 1 because both of these guys would cancel. If that happens, well, what got canceled? The x plus 2. So when would x plus 2 equal 0? Well, it's when x equals negative 2. So that's when we have a point of discontinuity, and it's right at that single point. And the asymptote is what's left. Well, we have an x minus 1. When would this equal 0? Well, that's when x equals 1, and so there's an asymptote at the line x equals 1. And that's how you find if something has an asymptote or a hole. So, I want you to try this one. Go ahead and try it on your own, and I'll put the answers up in just a second. Remember, you are going to have to factor it first. So, try it, see what cancels, see what's an asymptote, see what's a hole. Okay, when you factor it, you get x plus 1, x minus 1, and then on bottom you get x minus 1, x minus 5. And so you can see that the x minus 1 cancels. That means that we have a point of discontinuity at x equals 1, because if I was to plug in a 1 there, the whole thing would be 0. Now, x minus 5 does not cancel, so that means we have an asymptote at x equals 5. All right, let's go to the next page. So, when we go to actually graph these things, we need to determine if there are any asymptotes or holes and mark those on our graph. Then we're just going to make a table of values and start plotting points before and after those asymptotes to get a good graph. There is a way to determine where there is a horizontal asymptote, but we're not really focused on that. So for now, what I want you to do is just plot your points and see what the graph appears to be approaching, and then you can kind of use some deductive reasoning to figure out what your horizontal asymptote would be. So let's figure out, are there any asymptotes or holes in this one? Well, does anything cancel? Nothing cancels here, so there's no holes, but there is an asymptote when x equals 2, right? Because if I plug in a 2 here, the whole denominator is going to equal 0, so that's when the whole thing breaks down. So we know we have an asymptote at x equals 2. So we go over here, use blue, and we graph our asymptote. It could be a solid line, a dotted line, whatever you want. Doesn't really matter. All we know now is that we have this asymptote right here at x equals 2. It means our graph will never hit this line. It'll get really close one way or the other, but it'll never hit it. So we want a t-chart that's before and after 2. So x y, or you could say f of x. And we want a few numbers before 2, so like -1, 0, and 1. A few numbers after 2, like 3, 4, 5. And then also what I like to do is I like to pick the very extremes of the graph. And so maybe I should have done this up here, but I like to do -10 and +10 just to see where the graph is going to end up. And so I would just plug these numbers into this function and see what I get back. So go ahead and do that. Plug in -10, -1, 0, 1, 3, 4, 5, and 10, and see what you get back on your y's. And then we'll talk about plotting those points in just a second. Okay. When you plug these in, you should have gotten these numbers: 5, 6, 1/3, 0, -1, 3, 2, 5/3, and 5/4. So now we're just going to plot these points. If you plot these, you'll see what's going to happen here is you get this general curve downwards. It gets really, really close to this asymptote, but it never touches. And on this side, it starts up and it curves down. And you should also see that this number 5, 6 over here is really close to 1. And this number 5/4, which is way over here, is really close to 1 as well. It's a little bit over 1. This one's a little bit under 1. That means that we have a horizontal asymptote right at y equals 1. You can kind of just deduce that because you can see that they're both approaching that same number from both sides. There's another way to do that, to figure it out ahead of time, and if you catch on to the pattern, that's great, but I'm not really going to spend much time going over it. It mainly has to do with these coefficients, but really it's not that big of a deal. For you to know that, I'd rather you guys figure out the asymptotes from graphing it for now. Okay, so here's another one. I want you guys to do all the same steps that we did above. Remember, I got some steps right here. You can kind of look and see what I did, but try and graph this one. I'm going to pause the video and let you guys do it, and then I'll put the answer up in just a second. Okay, so you should have seen that there's an asymptote at x equals -2, and that there is no holes in this one because nothing cancels. I made my t-chart before and after -2, starting at -10 and ending at +10. Filled it in. I just did a few before -2 and a few after, just did the extremes. And then I plotted those points. And as I plotted those points, I saw this general curve. My blue line got messed up here. Sorry, that's a mistake with the iPad here. Sorry, everything got a little bit off. But the point is, as I graphed those numbers that I saw, you can just rewind if you want to look at them, but those numbers got closer and closer and closer to y equals 1 again. And you notice the coefficients are 1 over 1. The leading coefficients are 1 over 1. So that's how we could find that one. But you have that horizontal asymptote of y equals 1. Again, not very important that you are able to find that, but you should be able to see that that's happening, that these numbers are getting closer to 1 from on top and closer to 1 on bottom. And they're getting really close to this line, x equals -2. And then you got your general graph. I'm going to be looking for certain points, that you graph certain points accurately when I assess these graphs. So that's how you'll know what to do there. Okay. I want you guys go ahead and try this one. Factor it first and just determine if there's any holes or asymptotes. That's it. So just go ahead and try and factor it and see if there's any holes or asymptotes. Okay. You may have wanted to pause the video or whatever, see what I got. But I factored this guy, x plus 3 and x minus 3, and down on bottom it's x plus 3 and x plus 3. And we see the x plus 3's cancel. So the question here is, since I still have an x plus 3 on bottom, is this going to be a hole because it canceled, or an asymptote because it's still there? Well, the answer is it's going to be an asymptote. So if what you cancel ends up being the same thing as what's left, then it's going to just be an asymptote. So the asymptote wins, and we have an asymptote at x equals -3. We do not have a hole really in this graph. But I guess you could say the asymptote is a hole in a way. All right. So we're going to graph that at -3. And there's that. And hopefully by now you can predict, again, not that big of a deal if you can't, but hopefully by now you can predict what the horizontal asymptote is going to be, because we have a leading coefficient of 1, leading coefficient of 1. So it's probably going to be 1 over 1, or 1. I'm predicting that we have a horizontal asymptote right here at y equals 1. But even if I didn't know that, I could graph all of these and see what they approach. So I'm going to use this guy to graph, not this original one, because that's what canceling does. It just gives me something simpler to look at. These two things are essentially the same, It's just that this one has a hole at x equals -3, but it also has an asymptote, so we only need to graph the asymptote. Okay, so let's do x, let's do f of x, and let's do -10, and then a few numbers before my asymptote, which would be like -6, -5, -4, and a few after, -2, -1, 0. And then let's do one all the way to the end, that's 10. Okay, I think you guys can probably do this one on your own. So go ahead and fill this in and plot your points and get a good graph here. Hopefully you'll see that it's approaching that line, y equals 1. Okay, I'll put the answers up in just a second. Okay, if you fill out your t-chart, you should have got these numbers over here. And you can kind of see the shape as you plot them. And you can see, yeah, sure enough, this one does get closer and closer to that line, y equals 1. And there you go, we've graphed some rational functions. So, you guys can try this one completely on your own. I think you should be able to do it just fine. And I'll put the answer up in just a second. Okay, this one was a little bit funky. When I filled out my t-chart, this is what I got. And also, I got an asymptote at x equals 1 because after I canceled, I still had x minus 1 over on the bottom. But what I canceled was x plus 1, so that means that there's a hole at x equals -1. So I filled out my t-chart like normal, but I made special note that at -1, I knew there was a hole. So I filled out -1 in here. -1 over -1 minus 1 is -1/2. But because I know that there's a hole in there from this original equation, I graph a little empty circle right at that point instead of a line going through it, because that's what a hole looks like. And then I just fill in all the rest of the points like normal, and I got a graph. Now, if some of you guys are wondering what is the horizontal asymptote, it's actually going to end up being right here, and y equals 0. It's never going to touch that line. And that's because we have this special rule. When the degree on top is less than degree on bottom, degree on top less than degree on bottom, it's just at y equals 0. But if you would plot enough points, you could have seen that as well. Okay. Last thing I'm going to do is, this is 9.5, and all they really want you to do in 9.5 is to identify the type of each graph. So I'm just going to tell you the names of each of these real quick, and let you study those to just be able to identify them. So this first one is called a constant, because it's just y equals a constant number. This next one is called a linear function, and also we will call this direct variation. You'll learn that later. This is called the identity function because it's just y equals x. They're identical, so it's just y equals x. This one, you remember, is called a step function because they kind of look like steps. Also known as a greatest integer function. Okay, this one, whenever we get this V shape, that is an absolute value. Absolute value. And this one is a quadratic. It's a parabola graph, but we call it quadratic function. This one is simply a square root function. This is a rational. That's what we were just learning. And this one is also a rational function, but it's specific when there's just a number over an x. It's a very specific rational function known as an inverse or an inverse variation function. And so we're going to learn more in the next coming lessons about linear and direct variation and inverse variation. Okay, that's it for 9.3 and 9.5.